So we want to continue our study of light by talking about spectra. Now, what spectra is the resulting visual that we get when we take light coming from a source and we use a device that will break it up into its different parts. So whether it be a prism that allows us to see the different colors of the rainbow, or a more complicated device called a spectrometer that will do the same thing but allow us to see what that light is made up of, what different wavelengths, and separate them out so we can study them. There are three basic types of spectra. There is the continuous spectra, the emission spectra, which is sometimes called the bright line spectra, and the absorption spectra, which is sometimes called the dark line spectra. Continuous spectra is just what it sounds like. It looks like the rainbow. All the colors blend from one into the other. This type of spectra is going to be produced by a light bulb, by anything like a hot dense gas or a hot object that is heated up so that it glows. It's producing wavelengths of, it's producing all the different wavelengths, not just particular ones, and that's why you see all the different colors. Now, an emission spectra comes from a light where you have some gas, but it's relatively thin and it's heated up. And that gas is going to consist of different types of gases, maybe hydrogen gas, or maybe it's helium gas. And when you look at the spectra coming from that, you see just distinct bright lines of color. And what turns out, these lines of color are very distinctive for the light source. We call them a fingerprint. That is, every time we look at light of a particular type or made up of a particular element, it will show the exact same wavelengths of bright light. This picture helps illustrate what I'm trying to say. Notice that the lines from the helium source are very different from the sodium source, and also the neon bright line spectra or emission spectra is very different from the other two. And that allows us to actually identify the source of the light. The absorption spectra is sort of a combination of the two. The absorption spectra is like a continuous spectra, but then there has dark lines on it. Again, the dark lines appear at exactly the same wavelengths of what the bright lines would occur at. But what is happening is the light is shining through a thin cloud of gas, and instead of that gas emitting those wavelengths of light, it's actually taking them away, resulting in the black lines. So notice that we say, again, so this would tell us the identity of or the composition of the gas which is stealing the light away. So we want to try to understand this using or thinking at what's going on in the atom. How are these spectra produced? Specifically, we're thinking about the emission and the absorption spectra. So the first thing we have to remember is that the energy of a photon is directly related to the frequency. It's actually equal to a constant called Planck's constant, which is denoted by an h, times the frequency. So now we have to think and make sure we understand the atom. In the nucleus of the atom, we have protons and neutrons. And the element is determined by the number of protons in the nucleus. So an atom of oxygen has a different number of protons in its nucleus compared to an atom of carbon. Now, when you talk about carbon-12, that number 12 represents the total number of protons and neutrons. And so carbon can come in other forms like carbon-14, when we call those isotopes. So here in this picture, they're showing us the difference between the atomic number, which is the number of protons in the nucleus, and the atomic mass, which is the number of protons plus neutrons that are in the nucleus. Notice that at the top, we see that hydrogen, helium, and carbon all have different atomic numbers. They're all different from each other because they have different numbers of protons. When we talk about isotopes of, for instance, of carbon, they have different atomic mass numbers because they have different numbers of neutrons, but they all have 6 protons, making them carbon. In an atom, we know that the electrons, sometimes we think of them as orbiting around the nucleus, but basically they're anywhere around the nucleus, just kind of traveling around really fast. In this picture, what they're trying to show you here is sort of the relative probability of finding an electron at a certain location. So that means that very close to the nucleus, it's very likely that we're going to find the electron, where out here, where it's not as dense, the electron is less likely to be located. Atoms can have different energy levels depending on where the electrons are found. When a nucleus is relatively at a low energy state, which we call the ground state, the electrons are going to be relatively close to the nucleus like this. As the atom becomes excited, the electrons are more likely to move further away from the nucleus, and if a nucleus becomes, or an atom becomes ionized, the electron actually will gain so much energy that it can escape from the nucleus, and that's what we call ionization. What's interesting about the energy levels of the electron in an atom is that they are quantized. These two pictures here show the difference between what we mean by continuous and what we mean by quantized. This window washer has a stepladder, so he can only be on a particular step while he's washing the windows. The height that he can be at is quantized. He cannot stand in between 2 rungs of his ladder, while this window washer with his fancy pulleys and ropes can adjust himself to any height. He actually has continuous levels he can be at. The electron in an atom would be more analogous to this guy right here with the quantized heights. So we usually draw the levels or the energy levels of the electron like this, showing the fact that it can only be at very different levels, nowhere in between. As you go to higher energy levels, of course, you see the bigger numbers. Here, electron volts is just one way that we can measure energy. You might not have seen it before, but just think of it as just a new unit that you're learning about. When we're at the ground state, we can say that the energy is 0 electron volts. As we get to the very high point, this would actually be, if an electron got to higher than 13.6, it would actually be able to be escaped. Because of the way this is drawn, you would say that the electron can never be at 5 electron volts. There's no energy level there. Likewise, it could never be at 11, or any of these numbers. It can only be at these numbers that we see on the right-hand side. So we have to think about the rules of the energy levels. If an electron is in a particular energy level, it can only have that much energy, it can't have any less, and it can't have any more. If it wants to change energy levels, it either needs to absorb some energy or release some energy, so it can go to the next level. And this release or absorption is done through photons of light, which, remember, have a certain amount of energy. So, and if an electron in an atom goes from a high energy orbital to a lower energy one, well, what will happen? Well, think about it. If it needs to go to a lower energy level, it needs to get rid of some energy, and so it's going to release a photon of a very particular energy so it can drop down. That release is going to actually result in the emission of a light. So this is how an emission spectra happens. Different drops of energy will result in different wavelengths of photons being produced, and that's how we get the different colors. If an electron needs to go from a lower energy orbit to a higher energy one, that electron needs to absorb light or absorb a photon of a particular energy, and that helps you think about how the Absorption spectra would be formed because as that light is being absorbed, that results in an absence of those wavelengths of light, which ends up being a dark line in the spectra. Different energy jumps are going to result in different black lines at different wavelengths. So think about how you might be able to put this together to explain the production of emission and absorption spectra, which is sort of what I just explained. So when we look at this picture here, for instance, there are some jumps that can't happen. An electron cannot jump up this way because it's not going to another energy level. Likewise, this can't happen. But this one can actually, because this would just mean that the electron would escape. If an electron goes from this energy level to this energy level, it's going to gain 10.2 electron volts, which means it's absorbing a photon. So this is how an absorption spectra is being produced. For this drop, this is actually the release of a particular photon, and that's how emission spectra is going to be produced. The different colors of light, remember, are caused by different jumps, which represent different amounts of energy, which they also relate to different frequencies of light or frequencies of photons, which are different colors. The reason that the spectra are different for different elements is because of the fact that different elements have different energy levels. The energy level diagrams that you've been looking at are actually for hydrogen. If you have a different type of atom, those numbers will change, and that's why the transitions have different wavelengths, because the change in energy is different. We're going to talk about thermal radiation and the Doppler effect in the next video.